So go ahead.
Okay, so should I start?
Go ahead, yes.
Okay, sounds good. So first of all, let me make an update on yesterday's lecture. So there was a question about like who first proved universal optimality in one dimension. And then I mentioned that some people actually did it before Kohn and Kummer. So this is the paper that we've seen. So Vente Vogel and Nieboer, they're Dutch theoretical physicists. There is a paper in 1979, which as far as I can tell, so I don't vouch for correctness, but it's essentially proving optimality for Gaussian energy. So this is 1D universal optimality proof. And their proof is, well, at least some elements of it look similar to what Kohn and Kummer do, but not. So it's maybe it's not exactly the same. So it's a different proof. Yes, and then so another thing I wanted to say, there's some literature. So since there's basically going to be just a couple of hours spent describing modular forms and various properties of them, there's not nearly enough time to go into any amount of detail. So if you want to learn a little bit about them by yourself, so depending on how much time you want to invest, there's several nice resources. So if you're just interested in seeing modular forms in action, then there's a chapter in the book 1 to 3 of Modular Forms, a chapter by Don Zagier, who gives lots and lots of very down-to-earth and maybe some of them not so down-to-earth applications of modular forms. So if you just want to see like why people are interested in them, why they're so useful, this is a place to go. So if you want to actually like see all the details of proofs, all the complete statements, everything carefully carried out. So there's a recent book. So again, talking about very classical theory of modular forms, there's a lot of modern developments which will be much less accessible. But if you're interested in the classical theory, there's a book, Modular Forms: A Classical Approach by Henri Cohen. So not to mistake it with Henry Kohn. So and Frederick, I think, Stromberg. So it's a very long book, but it's very detailed, and it's so it actually explains everything in great detail. And if you have very little time and you just want to see a skeleton of the theory, well, you can read the chapter 7 in the course, A Course in Arithmetic by Serre. So it actually presents a lot of material in very little space, but it may not be as easy to go through. So it's very, it kind of assumes a little bit more about your background. Okay, and so another comment about yesterday's lecture. So there was a question about interpolation formula in dimension 1, and so I wrote something which was I thought approximately correct. So it wasn't the right statement. So the right statement is so this formula here. Oops. So the formula is saying that if you have a function, there are some additional properties on regularity, but roughly, if you have a function whose Fourier transform is supported in the interval from -1 to 1, then you can reconstruct it from the values of the function at integers and the values of the first derivative at integers. And the reconstruction kind of uses, well, it's this formula here, and basically it's squares of the cardinal sine function and like a linear function multiplied by that. So these are the basis function in this interpolation formula. And this is exactly what Kohn and Kummer used in the proof of universal optimality in dimension 1. So you use this formula to construct an optimal auxiliary function in their linear programming bound. Okay, so now with that out of the way, I'll go on to the topic. So today and tomorrow, I will briefly sketch the theory of modular forms in a very classical setting. And so, and also, I mean, so in addition to the literature, it's probably a good idea also to try to solve some of these exercises. So, so today's exercises don't really use any of the theory, and then tomorrow there will be something more relevant, actually, to the universal optimality problem. So all up to the Fourier interpolation formula used there, and then the day after that there will be something even closer to what is used in the proof of universal optimality. So, but it's these exercises are, if you want to learn more about modular forms, it's useful to do some of these exercises, or at least try to do them. Okay, so let me start again from the definition that I gave yesterday at the very end. So definition, well, okay, so before definition, so we're working with functions on the upper half plane. So these are just complex numbers with positive imaginary part. And so there is a group of biholomorphic automorphisms of this thing, which is PSL to R. And PSL to R, so it's a projective special linear group. So it's SL to R mod out by the kernel of this action, plus minus identity. And the action you probably all know very well. So if you have an element gamma in PSL to R, it acts, well, let's say tau, it acts on tau by a Möbius transformation. So that's the definition. And gamma here is a 2x2 matrix. In SL2R, but really, I mean, I will kind of abuse notation quite a bit. So I will talk about matrices or classes in this quotient interchangeably. So, and by restriction, so any subgroup of PSL to R also acts on the upper half plane. We just use the same formula for the action. So this is left action of SL to R on this set. And so what we're interested in is kind of in functions on H, which respect which play nicely with this action for some subgroups, for some discrete subgroups of PSL to R. And so, and actually for the whole of the course, there will be only two or three groups that we will consider. So first I will give a definition of so modular forms for gamma 1 and gamma 1. So here, maybe let me say gamma 1 is PSL to Z. So it's 2x2 matrices with determinant 1, with integer entries and modulo plus minus identity matrix. So modular form, or what more precisely, a holomorphic modular form of weight K, and K will be always, well, almost always, it will usually be an even integer. It makes the theory very, very pleasant to work with. So there, but unfortunately, sometimes you have to work with other weights. So homomorphic modular form of weight K is a holomorphic function function f on the upper half plane such that and then there are two conditions. So first, you want it to respect this Möbius transformation so you want it to be kind of invariant under Möbius transformations in this group PSL to Z, except, well, not quite invariant. So you put this additional factor on the right. And so this is the main the main property in SL2Z or in PSL2Z, as I've been saying, I've abused this quite a bit, this notation. So, and the second property is you want it to have a Fourier extension without a pole at infinity, whatever that means at the moment. So maybe a little bit vague. So basically you want it to be of the following type, where AN are some complex numbers, and Q is a notation which is very useful, is to e to the power 2 pi I tau. So it's a basic one periodic complex analytic function. And just to say, I will use this notation quite freely. So if you have Q to some power A, you think of it, even if A is not an integer, it's perfectly well defined if you think about it as a function of the upper half plane. So there's no like principal branch that you have to take. It's already done for you because this is the universal covering over the puncture disk. So it's just e to the 2 pi I A tau. For A in, well, it can be a real number, but let's say rational. Okay.
Can I ask a question?
Yes.
So in the transformation rule, why do you only want the denominator to appear?
So there's okay, so I will explain a little bit about this transformation rule. So you want something which actually has respects the group composition well. And if you because this thing is an action on the left, so the expression here, you can take a composition of two matrices, and you want this factor here to behave well with respect to composition of matrices. And it turns out that basically this is the most natural way of making this compatible. So, but there is a better explanation. So in a moment I will give a few maybe more motivating reasons why it's only the denominator that appears. So roughly the reason why the denominator appears is because if you think about gamma tau, a fractional linear transformation, it's and ABCD is in SL2, then gamma prime of tau is just 1 over c tau plus d squared. And this is really the reason why this vector appears and not the numerator. Okay. So let me make a few comments, right, before I even delve into examples. So first comment is there is a group action involved, which maybe is a little bit hidden. So it's you can define kind of a slash operator in weight k, and this is I mean it makes some definitions much easier to work with. So you just define it as a function c tau plus d to the power minus k f a tau plus b over c tau plus d. So again, I'll usually gamma will just denote this matrix. So this thing, so slash k defines a right action of PSL to R. And here, so this actually here, it's important that k is an even integer, because otherwise it would not be, it wouldn't respect this projective invariance on the space of all functions on upper half plane, on functions from H to C. Doesn't need to be holomorphic, just any function. This formula defines a group action. And so, and in terms of this group action, the condition 1 is very natural. It just tells you that F is invariant under this.
Danylo, there is a question from the audience.
Yes?
Could you repeat why
k has to be an even integer.
In this, well, there is a way to define things for odd integers, for example, but then it actually is not BSL2R, it has to be SL2R. Because it's kind of a subtlety, so let's just, there are plenty of modular forms of odd weights and even half integral weights, but then the definition needs to be changed a little bit. So for the purpose of all these lectures, I will usually work with PSL2R because this thing acts faithfully on the upper half plane, and SL2R has non-trivial kernel. So actually, if you look at the definition the way I gave it here, if k is odd, it immediately gives you that f has to be a zero function if you just plug in -1, 0, 0, -1. So for A, B, C, D, this will be f of tau. This this thing is f of tau. This thing is f of tau, and this thing is not, is -1, -1. So it kind of makes, so this definition is just not the right thing to use for general theory, but for the purpose of this course, Minicourse, it's just, it's easier to only work with even weights.
Thank you.
Okay. So this was the first comment, so it means that 1 is equivalent to saying that f/k gamma is equal to f for all gamma in PSL to Z. And the condition 2, well, so at the moment it's perfectly fine. When we talk about other groups, I mean, there will be only a few other groups that I'm interested in, but so condition 2, you can think of it equivalently as f/k gamma is polynomially bounded at infinity. For every gamma in PSL to Z. And you may think, well, if you know 1, why would I write it this way? But the reason is, so there is a definition of modular forms for a subgroup of finite index in PSL to Z, and then this condition is more natural than forcing this Fourier expansion at every cusp. Well, I mean, forcing this Fourier condition is a little bit, I haven't said what the cusp are, but yeah, this condition is a bit harder to generalize directly, but this can also be done. So, and this polynomially bounded at infinity, I hope roughly it's clear what it means. So if you take this function, approach infinity, so it doesn't grow faster than polynomial in the height, so in the y variable. So, and there's actually an exercise in the sheet for today's session that basically says something about this polynomial boundedness at infinity. Okay, so let's move on. So what I want to do now is maybe a comment about why this definition. So why this weight k additional factor appears, and why would you want to consider this? So basically, you may think of so modular forms are homogeneous functions of 2D lattices in C. And so what I want to say by this, so if you have a lattice lambda, let's say you write it like this. So where omega 1 and omega 2 are at C. And you make the basis oriented. So in my case, this would mean that omega 1 over omega 2 has imaginary part greater than 0. So that would make the basis omega 1, omega 2, maybe omega 2, omega 1, positively oriented. And so what you want to do is you want to define somehow a function of a lattice lambda to be some function of omega 1, omega 2, and you want somehow to know that if you choose a different basis, then this value doesn't change. And so first let's say we want to have a function f of lambda such that it is invariant under rescaling the lattice by any complex number. So that would be kind of including both rotations and homotheties of lattices. So then it's natural to take, instead of a function in two variables, actually a function in just the ratio of the two things of omega 1 and omega 2. And that function, so if you think about, so it's well defined, so f is well defined, meaning that it doesn't depend on the choice of the basis, if and only if f of a tau plus b over c tau plus d is equal to f of tau for all matrices A, B, C, D in SL2Z. So these basically tell you, well, what are the changes of basis in the lattice are. And then if you, instead of this kind of invariant condition, if you want functions that are homogeneous, so that if you rescale the lattice, you get an expression of the other way around. It's a little bit confusing. So if you want this thing, then this condition, again, you define a function in one variable, but then you have to put also omega 2 to the power minus k, and then the condition that, so f is a well-defined function of lattices, well-defined, is if and only if f, f satisfies, so f slash k gamma is f for all gamma in SL2Z. And again, I'm abusing notation a bit, so it's PSL2Z or SL2Z, but here it doesn't really matter. So really, this condition is quite natural if you think about these functions as functions on the space of lattices, which you want them not only to depend on the geometry, not on the actual basis choice. Okay, and so another small comment before I start giving examples is if you so this condition, so for example, f is a modular form of weight 2. It's the same as to say that this object is gamma SL2Z invariant. So this differential form. Because if you think about what the change of variables does to this differential form, it exactly gives you the c tau plus d squared factor. If you look at, so this is this computation I did here. The derivative of the Minicourse transformation is c tau plus d to the power minus 2. And analogously, so you think weight k, formally you can think about this as an object of this type. Well, I mean, you don't have to think too much about what this actually means. So you think about this as some formal expression, but you can interpret it as a section of some line bond. So it's, but that's maybe a little bit more highbrow than what I want to do. Okay. So let's fix some notation. So mk of gamma 1 is a space of all of holomorphic modular forms of weight k. And so later today, I hope I will have enough time to show that these spaces are always finite dimensional. So, and so, well, first of all, it's a vector space because if you add functions which satisfy the same transformation property, you again get functions that satisfy them. Also, you can multiply things, and if you multiply, so if you multiply So let's think ML. So you take a function of weight k and function of weight L. So it's just I don't know, dot product or usual product. So just product of functions gives you a function mk plus L. So you get a modular form of weight k plus L. And so basically what one can do is if you take the direct sum over all even integers of these spaces, this is a graded ring. And basically the goal of today is to show that it's isomorphic to a ring a ring of polynomials in two variables E4 and E6, where this is something of weight 4 and this is something of weight 6. So for gamma 1, basically there's a very simple structure for all of modular forms. So whenever you have a modular form of some weight, you know it can be written as a polynomial in certain two special modular forms. So let me actually define some examples. And on a certain level, like the reason why modular forms are so useful is that there's very many different constructions of modular forms. But all of these objects, all of these different constructions, they live in small finite dimensional spaces. So you get non-trivial overlaps between these things, which if you think about them in terms of the constructions themselves, it's very hard to see why these objects should be the same. But because they land in the same small finite dimensional space, they often coincide. And we'll see a few examples today and tomorrow, which are maybe quite striking if you've never seen this theory. So now let me give lots of examples. And some of them I will prove that they're actually modular forms if I have time. So, and there's three basic sources of modular forms. And one of them is so-called Eisenstein series. And the Eisenstein series, so I will first not give the right definition. I will just write what the Fourier expansion is. So it's a function with the following Fourier expansion. So I want to explain what these numbers are. So sigma S of n is just the sum of S powers of divisors of n. And bk are Bernoulli numbers. So I mean, there's many ways of defining them, but the easiest is just to give the generating series. So these are the coefficients of this function, Taylor coefficients of the x divided by x e to the x minus 1. Okay, so I don't know if I will have enough time to show, but these are, so gk for k even and k greater than 2, these are modular forms. So just to give you a few examples, and there's also kind of a competing normalization. So sometimes it's convenient to have the coefficient in front of q to be 1, and sometimes it's convenient to have the constant term to be 1. So what one does, there's actually two kind of normalizations in the literature. And this is absolutely terrible because there is also the exceptional root systems of type E, and this E has nothing to do with that, but we will see soon that there's kind of a source of confusion, which is E4 will have something to do with E8, and these two E's are quite different. So the other way is we just divide by the constant term and write it this way. Okay. And so, so just give so these are the E4 and E6 that I mentioned in the structure theorem above. So E4 has Fourier expansion starting with these numbers, and E6 is, let me make sure I do it correctly. It's 16. So it doesn't really matter for me that this is the number, but since I gave two terms for the first one, I wanted to give 2 terms for the next one. So, and the theorem tells you more or less that everything can be written in terms of E4 and E6. So the theorem that I mentioned above. So this is a theorem, and maybe I will have enough time to prove it. So this is one source of examples, but there are many other sources. So another another big source of examples, so-called Theta Quotients. And I won't go into much detail, but I'll just give a few examples. So there is a famous Ramanujan delta function, which has a completely random-looking definition. So it's q times the infinite product of 1 minus q to the n to the power 24. And this thing is in M12, gamma 1. But actually, I want to say, now I want to define the subspace of that, so S12. And I just define Sk of gamma 1. So it's functions in Mk gamma 1 such that f is equal to so it's big O of q in the Fourier expansion. So what this means is that at infinity this thing vanishes. So if you think about we go higher and higher, this thing will vanish. So this is something that's called cusp forms. And they play a very important role in many arithmetic aspects of the theory. So, but really, so why? So I said the word eta, and this is delta. So what is eta of tau is a 24th root of this function, and in a certain sense, it's a much more fundamental object, but it's not a modular form in the way I defined because it has a multiplier system. So this is a form of weight 1/2 for gamma 1, but with some multiplier system. And they have, since I haven't defined what it is, I won't talk much about it. But roughly, oops. So let me skip this thing for now. So roughly, eta has 2 transformation laws, and one of them, it's not periodic because it has this q to the power 1/24, but it's, well, if you translate it by 1, you just get this 24th root of unity. And it has this non-trivial transformation that tells you if you take -1/tau, so this Möbius transformation, you get, I mean, that's how it transforms. So, and if you think about the definition, it kind of looks similar to what we had before. So this would be the c tau plus d, except it has an I in it, and you have a non-integral power of it. So, so again, I don't want to go too much into detail regarding eta. What else? What else? So there is also theta functions. That will be a main topic tomorrow. Theta functions of lattices. And this, so I will be very brief now, but basically it's a function which counts the vectors of each length in the theta function, in the lattice. So it's a sum over all elements in the lattice. Let's say lattice is some, so it's not necessarily 2-dimensional, so it's some in a d-dimensional space. And you just count q, you just put q to the power absolute value squared of x divided by 2. So I mean, this divided by 2 kind of is optional, so that will just change the group on which this thing will be a modular form. So this is modular form of weight d over 2 for some group, for some subgroup of gamma 1. So I haven't quite told you what a modular form for a subgroup is. So let me briefly explain that. So so mk, so let's say gamma in gamma 1 is a subgroup of finite index. Then basically I already kind of said. So first you want so mk of gamma 1. So function is a modular form of weight k for the group gamma. Sorry. So this is if and only if two conditions hold. So again, you require this gamma invariance, but now for all elements in the smaller group, and you require this polynomially bounded at infinity for all gamma in SL2Z. And previously, both of these groups were the same, so it was kind of silly because I said infinitely many conditions here, which were all the same, but now these are actually different. So this is the definition of what a modular form for a subgroup of SL2Z is. And for the rest of the course, the only groups that I will talk about are congruence subgroups, and basically there will be just a few. Well, essentially just one that I'm interested in. So let me just define that. So it's something called the principal congruence subgroup of level n. And it's just all matrices which are congruent modulo n to the identity. And then there's another, well, for the theta story, for the story with theta functions, you actually define a different group where you put this congruence condition. You just require the lower left entry to be 0 modulo n, not n. And then there's a theorem, which I'll talk about maybe tomorrow, that theta lambda tau is modular of weight d over 2 for some gamma not n, so for some group of this type. But the tricky part is, so lambda has to be integral. And then there's a recipe so for any integral lattice. And then there's actually a recipe for telling you, if you know the lattice, what is this level. So this n for which it is a modular form. Okay, so just to give one example, if you look at the lambda, the E8 lattice, there's this coincidence that I was talking about, that since their spaces are small and constructions are plentiful, it turns out that this is, so the theta function is equal to E4 of tau that I already showed before. And this is where this kind of terrible notation comes up, where E4 is the theta function of E8. This E4 has nothing to do with E8. So it's even worse because there is an E8, of course, the Eisenstein series. And then the E8, the lattice, so it's better not to confuse them. Okay. So, and finally, maybe, so there's a few more, deeper examples, I guess. So there's examples from algebraic geometry. And I will just give one example. So so this is related to the so-called modularity conjecture, which was proven well in early 2000s, but it was so special cases of that were used by Wiles to prove Fermat's last theorem. So if you look at this this function f of tau is the product of eta squared tau and eta squared of 11 tau, and eta is this eta function I defined before. So you can expand it. You see it has let me check that I don't give the wrong formula. So it has the following Q expansion. Seven plus dot dot dot. And so what this modularity theorem tells you in this special case is if you look, so if you say this is sum a n q to the n from 1 to infinity, then AP for P prime, well, okay, so AP is equal to P minus number of solutions x and y modulo P of the equation y squared plus y is equal to x cubed minus x. So this is, yeah, the number of points on some elliptic curve. And it turns out that these point counting on some varieties often have something to do with modular forms. And in this case, this is like the relation. And in fact, one can kind of go further, and so you can start with some elliptic curve, and then you can define a modular form. This is very, very complicated, so non-advanced. And so let me see. And then there's actually lots and lots of other constructions which are less known. So something maybe I want to tell. So something called toric modular forms. And this is so I'll just give an example of what a toric modular form without explaining what it is. So tk plus 1 t 2k plus 1 tau. There is a definition which is much more general, but one of the special cases is the following thing. So you take just this combinatorial series. And it turns out for somewhat, there is an elementary proof and then there is a very highbrow proof, but this is a modular form of weight 2k on gamma naught 2. And so in principle, there are other ways of writing all modular forms on gamma naught 2. And from this fact, you can derive some non-trivial combinatorial identities. So if you just expand this thing out, you'll get some funny summation formulas for over some cones, so certain piecewise linear, piecewise polynomial functions. Okay, so now let's go back to proving something. So first of all, so something that is already in the exercises. So this group, PSL2Z, is actually, you can describe it abstractly. So it's generated by two elements T and S, and this will be very useful notation. So T is just this matrix, upper triangular matrix with all ones, and it corresponds to the Möbius transformation that just sends tau to tau plus 1. And this is where you actually see that you want periodic functions only. So this tells you that all modular forms are periodic functions. And S is this matrix that corresponds to the inversion or rotation by pi over the imaginary unit. So it's just this Möbius transformation. Sorry. So in principle, since the condition that we have is f slash k of gamma is equal to f for all gamma, and this operation slashing with gamma is a right group action, it's sufficient to check it only on the generators. So it means that if you want to prove that f is an modular form for gamma 1, it suffices to check that f is periodic, which is usually, like by definition, it is periodic. And the other property is you want f at minus 1 over tau is tau to the k times f of tau. Okay. So now let me say a few words about the geometry of this whole situation. So this group, this group acting on upper half plane, it's acting properly discontinuously, but it has some points which are stabilized by some non-trivial elements. And so what you have here in this picture is a fundamental domain for this group action. So it's something that's called the standard fundamental domain for the group gamma 1. And it's every point in the strip between minus a half and a half that has absolute value at least 1. So it's this region F here. So it's the fundamental domain. And so there's a few points which are interesting. So point I has a non-trivial stabilizer. So I is fixed by S. So this matrix S that I wrote, and rho is fixed by I guess ST. And so this is an element of order 2. This is an element of order 3. So the stabilizers are of order 2 and 3. And so because of this fact, there's many statements which become more complicated because not all points in the upper half plane are the same with respect to the section. So some of them you have to add to them this weight 1/2 or 1/3. And also, so this is kind of an infinite strip, and at infinity you have well, what is called the cusp at infinity. So you can't really see it from this picture because it's infinitely far, but if you think about another fundamental domain, so if you flip this thing around, you will get this picture, and then this will be the cusp. So that's hence why that's where the name comes from. Okay, so and then so this is basically telling you how group elements may produce a tiling of the upper half plane by copies of this fundamental domain. So here you have the identity element, so that's the fundamental domain itself. If you translate it by 1, you get this thing. If you translate it by -1, you get this thing. Then you can flip it, and then basically you can decompose every point. So every point on the upper half plane falls into exactly one of these regions. And except for the boundary, that it's very nice decomposition. Okay, so now let me state a theorem. So I don't know, when did I start? At 20 past?
So basically you are at 1 hour and 1 minute.
No, but we started late.
No, 51 minutes.
Okay, so maybe let's take a small break, and I'll formulate theorems, and then I will take a little bit of time from the exercise session, and then we will do the exercises. But let's take a break now.
10 minutes?
Yeah.
Okay. I wanted to ask, is there a link between the representations of SL2, something like the Peter-Weil theorem, and with modular forms, that any function can be decomposed in modular forms if it is, I mean, something kind.
Well, yeah, there is. I mean, I guess that would be more like not working with holomorphic functions, but with like L2 integrable functions, and then you want to decompose it into some representations. So this is what modern automorphic form theory does. It does a lot of representation theoretics, things like that. So yeah, there's a lot of links, but if you work only with holomorphic functions, it's almost impossible to see such results.
Right. Okay.
Okay, so let's continue. So I'll take a little bit of time from the exercise session. So there's one theorem that I want to outline, and that's very important. So it tells you both some structural properties of these functions, and also it tells you that the spaces, it gives you a proof that the spaces are finite dimensional. Actually, it tells you what the dimension is. And so I'll start with that. So, but before I formulate, so there's few observations. So first of all, well, we define so the order of vanishing of f is just the usual order of zero, order of zero, f at point z. And so the functions themselves, so modular forms, are not gamma invariant, but the order of vanishing is still well defined because this kind of fudge factor cz plus t to the power k, it's not vanishing anywhere on the upper half plane. So whatever point you look at, the order of vanishing will not change. So ord z of f is invariant. So if you map z to any other point by an element PSL to z, it doesn't change. And also, so there is something you have to do with these strange points I and rho. So the easiest way is to define a multiplier, or also like weight. So define it to be 1 if z is not in the orbit of I or the orbit of rho. 2 if z is in the orbit of I, and 3 if z is in the orbit of rho. Well, alternatively, you can define it as the order of the stabilizer. So it's number of elements in stabilizer of z in PSL to z. And so with that, there's a formula. So that basically, if you take all the zeros of a modular function, modular form, they cannot be completely arbitrary, and they have to satisfy a certain strong condition. And the theorem is as follows. Sorry, and also I need to define what the order at infinity is. It's just the minimum n such that the coefficient is non-zero. So it's roughly what the order of vanishing is for the function of q, if you think of q sending q at the origin. Okay, so now theorem that I want to state is theorem. So for any f, a modular form of weight k for gamma 1, f non-zero, there is a following identity. So if you take a sum over all kind of representatives of upper half plane modulo the group action of PSL to z, so and you sum order of vanishing of this function divided by this weight, and plus you add the order of vanishing at infinity, then this actually doesn't depend on f. It's always equal to k over the weight divided by 12. And so the way to prove this, so I won't do the calculation, but I will tell what you have to do. So you integrate, well, the logarithmic derivative of f over something that some people call Swiss cheese contour. And so let me show you what this Swiss cheese contour looks like. So basically you take the fundamental domain, you cut it off at some height, some height t, and you also drill holes everywhere where there are zeros of your function. And possibly if it has a zero at these corners, you also make a hole there. So this is I, this is rho, and this is it's -1 overall. And so, and what you do is you just integrate over this contour and look at what Cauchy's theorem tells you. And so for each of these, so these are the zeros of your function. So for each of the zeros inside the domain, you pick up multiplicity 1 so you just pick up 1 for the residue. For each zero on these vertical lines, you also get exactly 1, because they have kind of, you have 2 parts of the circle. It's just translated. And then for I and rho, the calculation is a little bit more complicated. So you have to make a change of variable, like a Möbius transformation, send this point by a fractional linear transformation to a disk. And then you figure out that if you, so because of the transformation properties of modular forms, even if you integrate over a third of a circle or over half of a circle, you still pick up the, I mean, you still get like essentially a full integral of a circle because of some symmetries. So this is why you get these 1/3 and 1/2 multiples. And then so this bit tells you the order at infinity of f when you integrate, and then every other contribution to the contour integral either cancels out or it contributes actually this k over 12. So k over 12. This gives you, you get it from this semicircles, from this arc on the circle. So this is roughly how you prove this. So, but I have to skip that. But the corollary is you get an upper bound for the dimension of modular forms. And it's, well, it's either fractional part of k over 12 plus 1, or it's fractional, it's floor of k over 12. And so this happens whenever k is not congruent to 2 mod 12, and this happens when k is congruent to 2 mod 12. And so you basically what you have to do is you use this theorem and you assume that the space has dimension larger than this. And then you just, by some linear algebra, you come up with a linear combination of your independent functions, which vanishes more often than it is allowed by this formula. So I will not do that, although we can do it as an exercise. And so let me just finish by telling you, so you have basically, let's make a small table. So let's put k here, and then the dimension of mk comma 1, well, at least an upper bound. But you will easily see that actually this upper bound is attained. So I'll go from 0, 2, 4, 6, 8, 10, 16. And so actually first corollary of the theorem here is actually there's nothing in negative weight. So because otherwise you get some silly contradiction here. So and another small corollary is that this dimension is 0 if k is negative. So you only have to look at non-negative weights. And here, well, dimension is 1, but it's, you know, it's 1 because the constant is an example. So here the upper bound that you have from this corollary is 0. And then you know it is 0 because that's the smallest it can be. So here the upper bound is 1, 1, 1, 2, 1, 2, and so on. So what I want to say is that, well, if you believe for the moment that E4, if you believe that E4 and E6 are modular, and you believe that there is no non-trivial relation between them, then you can already see that this theorem is tight, because here, well, you see you have E4 here, you have E6 here, you have E4 squared here, you have E4 times E6 here. So here everything is attained, so you have exactly one form and the upper bound is 1. So here you have E4 cubed, but you also have E6 squared, so you have 2 functions, and actually they are linearly independent. And similarly here, you only have one function, which is E4 squared E6. And then here you have, again, 2. So I guess you have E4 to the power 4, and then E4 times E6 squared. and so on. And actually, it's a small, again, exercise to show that, well, if you know these upper bounds, you actually, the polynomials in E4 and E6 of homogeneous weight K exactly give you this many independent functions. So the only part that I'm not saying how to prove is that E4 and E6 are algebraically independent as functions. Independent, I mean, over C, I guess. So they don't satisfy any non-trivial relations, so at no point will you have fewer functions than you can come up with. And this is, well, maybe let's leave it as an exercise. And so one other thing that I forgot to do is actually, I never told you about one very important function, which is called so-called J invariant. And this is a function that you just defined by taking E4 and dividing it by delta. And so it has the following Q expansion. Let me give you one more term. Yeah. And so, I mean, it won't play any role in what I'm going to talk about later, but these numbers actually are very special. So they have something to do with monster group. This is so-called monster moonshine. And there's a priori no obvious reason why these modular forms should have, modular functions should have anything to do with finite groups. And this, so this is an example of a modular function, which I haven't quite properly defined. So it's just a modular form of weight 0, but we allow negative coefficient, negative powers of Q in the Q extension, because otherwise there will not be an interesting example of such things. We allow f of tau to have, so we just want finitely many negative Fourier coefficients to be non-zero. So this is this notation. Okay. So this J is actually crucial, and it will play an important role later. Well, also, I mean, delta is also important, but yeah. So, okay, so let me stop here and maybe we can do some exercises.
Okay. Are there any questions?
Oh yeah, actually, questions are also fine.
There are no questions. Okay, since that there are no questions, so let's set thanks, and then let's set up the exercise. So I'm going to stop this.